For decades, one of the biggest, most fundamental questions in all of physics has been surprisingly simple. What is most of the universe actually made of? We can see its gravity everywhere. It's the stuff holding entire galaxies together. But the substance itself, it's completely, utterly invisible. So today, we're going to dive deep into this enduring cosmic mystery. And the scale of this problem is just staggering. Seriously. Everything we can see and touch, all the stars, the planets, the galaxies, you and me, that's all just ordinary matter. And it turns out that only accounts for about 15% of all the matter in the cosmos. The other 85%? That's the giant missing piece of the puzzle we call dark matter.
For the longest time, the leading suspect was a type of particle called a WIMP, a weakly interacting massive particle. Seemed like a good bet. But after years and years of searching in these super deep underground labs and in giant colliders, we found absolutely nothing, not a single trace. And as this quote gets at, these null results have really forced physicists to get creative and start exploring much more, unconventional ideas.
So here's our roadmap for this journey. First, we'll unpack the mystery itself. Then, we'll go beyond the usual suspects and explore a pretty wild theory about how something called dark quark nuggets could have formed. We'll even meet a prime suspect, the sexaquark. And we're going to end with a truly startling possibility. What if a clue to dark matter has been right here on Earth this whole time? Okay, so here's the bottom line. When we look out at galaxies, we see them spinning, but they're spinning so incredibly fast that they should be flying apart. The gravity from all the stars and gas we can actually see just isn't nearly enough to hold them together. There has to be this huge amount of unseen mass providing the extra gravitational glue. That's dark matter. Now, you might be thinking, couldn't this just be normal stuff that's just hard to see? Like giant dust clouds or dead stars? And that's a great question. It's a very logical one. But it turns out our best models of the universe, of cosmology, tell us the answer is a pretty firm no. Let's dig into why that is.
So this is where a really fundamental distinction comes in. All the normal stuff in the universe, which physicists call baryonic matter, is made of particles from the Standard Model, our rulebook for physics. We're talking protons, neutrons, all that jazz. And crucially, it interacts with light, which is, why we can see it. But our models of the Big Bang predict exactly how much of this baryonic matter should exist, and it's not even close to being enough. The dark matter has to be non-baryonic, something totally new, something that lives outside the Standard Model.
And this is where the ideas start getting really interesting. What if dark matter isn't a vast sea of tiny individual particles at all? What if it's actually made of huge composite objects, sometimes called macros, just roaming the cosmos? And when I say huge, I mean these things could range in mass from less than a gram to heavier than an asteroid. So, if these massive objects are real, how in the world could they have possibly formed? Well, the answer takes us all the way back to the fiery, chaotic first moments right after the Big Bang. The whole theory behind this hinges on a fascinating concept called dark QCD. The idea is that there's a whole parallel version of the strong nuclear force out there. That's the force that glues quarks together into protons and neutrons in our world. This dark sector would have its own dark quarks and dark gluons, operating with their own rules, completely separate from our own. Okay, for these dark quark nuggets to actually form, three very specific things had to happen in the early universe. First, you need what's called a first-order phase transition. Think of it like water freezing into ice. It doesn't happen smoothly, it happens suddenly. Bubbles of this new dark phase would form in the hot soup of the universe. Second, some kind of property, a dark charge, had to get trapped inside these bubbles. And finally, just like our universe has way more matter than antimatter, this dark sector needed a similar imbalance. Otherwise, the nuggets would have just annihilated themselves out of existence right away.
This theoretical framework is, it's incredible. And it points to a very specific and, let's be honest, a very strange candidate for what these dark nuggets could be made of. A particle called the sexaquark.
Yep, you heard that right, a sexaquark. Not three quarks like the protons and neutrons were all made of, but six quarks all bound together into a single, stable particle. To be specific, 2 up quarks, 2 down quarks, and 2 strange quarks. It's a totally unique state of matter that's possible in theory, but has never, ever been definitively observed.
And its properties make it the perfect cosmic ghost. As a particle, it would be electrically neutral, so it wouldn't leave a track in a particle detector. It doesn't interact with light, which makes it truly invisible. And its predicted mass is so close to a regular old neutron that telling the difference would be incredibly hard. It's the perfect phantom particle.
And believe me, scientists have looked. Major experiments, including the big ones at the Large Hadron Collider, have searched for any sign of the sexaquark. But as the research shows, when they look at the data, the final results are just empty histograms. No bump, no signal, nothing, which only makes this elusive particle even more mysterious.
So we've searched the vastness of the cosmos, and we've searched inside the world's most powerful particle colliders, and come up empty-handed. But what if a clue has been right under our noses, or maybe right above our heads this whole time?
This is where the theory takes a really mind-bending turn. It connects the cosmic scale problem of dark matter to a mysterious phenomenon that has baffled people right here on Earth for hundreds of years.
Physicist Ariel Zhitnitsky put forward a really bold proposal that connects these dots. His theory suggests that the early universe didn't just create dark matter nuggets, but also dark antimatter nuggets, which he calls anti-quark nuggets, or AQNs. He proposes that when one of these extremely rare antimatter nuggets comes streaking in from space and slams into our atmosphere, the resulting annihilation event is what people have been reporting for centuries as ball lightning.
And what's really remarkable is how well this wild theory lines up with what eyewitnesses have said about ball lightning for years. The enormous energy release, well, that's explained by matter-antimatter annihilation. It's consistent with strange radiation signatures that have sometimes been detected nearby. It could explain the bizarre shapes and the erratic movements people report. And of course, it would perfectly explain why the phenomenon is so rare and unpredictable. It only happens when one of these tiny antimatter bullets from deep space happens to hit our atmosphere in just the right place.
The implications of this are just profound. This isn't just a theory about some weird weather. It's a framework that connects the largest structures in the universe to a mysterious phenomenon in our own backyard. If this theory ever gets validated, it wouldn't just solve the puzzle of ball lightning. It would mean that a direct manifestation of dark matter physics is happening right here on Earth, completely revolutionizing our entire understanding of the universe and our place within it.